And away we go into the third podcast of Chemistry 30 Week 9. Now, last podcast, we examined Le Chatelet's principle and how equilibriums would respond to changes in concentration or the addition or removal of a reactant or product. This time, we're going to focus on changes in temperature. And I want you to think back to Unit 1 in the context of temperature, because this is going to work into, of course, an endothermic reaction versus an exothermic reaction. I want to remind you of a few things in relation to this. With an endothermic reaction, we have energy, and that would be like our enthalpy change, right, is a reactant, right? And when energy is a reactant, if we write it separately, we write it as a positive change in enthalpy. Vice versa, when we've got an exothermic reaction, that's our scenario where energy is a product. If the energy is a product, thinking back to that first unit, it is written as a negative delta H. Not within the context of the reaction itself, but if delta H is written off to the side. Now, guys, if you heat up a system, naturally, what's going to happen is the reaction wants to use up the energy. Well, how do you use up energy? Well, energy will act as a reactant. So heating up a system will always favor energy as a reactant, which is endothermic. Vice versa, if we cool down a system, it's the opposite. The reaction, think of it like it gets cold and it's trying to produce more energy. If you take away energy, what's the opposite of that? Producing more. How do you produce energy? How do you make it exit the system? You have an exothermic reaction. So have those in the back of your head, please, 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 as we continue to analyze this. Here's another way to look at it. From an endothermic perspective, if I heat up the system, then we're going to have reactant A, say, plus reactant B. It is a equilibrium type system, produces reactant C and reactant D. And then I'm going to put plus our delta H. If I increase the temperature, naturally the reaction then is going to look at that and it is going to favor the reverse. It's going to go backwards to try to use it up. Okay? Think of the logic of that. That would be the endothermic reaction. The reverse reaction, the way that I drew this, is endothermic. The forwards reaction is exothermic. I'll say that again. In this A plus B equilibrium to C and D scenario, the reverse reaction is an endothermic one, right? Energy plus D plus C produces B plus A. Vice versa, the forwards reaction is an exothermic one. A plus B produces C plus D and energy. Okay, let's look at it again in the context of cooling it down. If I've got A plus B at equilibrium producing C and D plus delta H. Take that delta H, and this time I'm going to take some heat away, reduce it. Naturally, the system wants more energy because that's the opposite of taking it away. So in this particular scenario, it's going to favor then the forwards. Every reaction is going to be unique depending upon its enthalpy change. So keep that in mind. Okay, let's keep going. What if we have these two particular systems? Now, you don't have these examples in your written notes, but I just want you to think about them and think about the logic of them. Take this first one. And what if I do the scenario where I heat the system up? If I heat the system, is this going to favor the forwards reaction or the reverse? Well, if I heat it, I'm adding energy. What does the system want to do? If I add it, it naturally wants to get rid of it because that's the opposite. That's what Le Chatelet's principle states, is that an equilibrium will always respond to oppose the change. So I increase energy, the system naturally wants to get rid of it, to decrease it. Well, that means we need energy to react. Therefore, it is going to favor the forwards, the reaction. It favors the products. Now, let's look at another scenario. Number 2. What if I cool this system? If I cool this system, that means I'm taking away energy. What does the system want then? The system wants to oppose that change. So it's going to try to produce energy. In this case, energy is produced as a product. It's an exothermic reaction. So if I cool it down, this is also a favoring of a forwards reaction. Okay? Think about the logic. It's always about opposing the stress put on a system. Now, this example is the one that you have in your notes. Now, something's missing here, though. We're going to analyze these from the perspective of temperature changes, so heating a system or cooling a system. But at this point, you have no idea if it's exothermic or endothermic. You will be faced with this in the context of the questions in your assignment. Now, you actually have the tools to deal with it. That's going back to Unit 1. How do you figure out what the enthalpy change is for a balanced chemical reaction if it's not given to you? Ding, ding, ding. Hopefully you said Hess's Law. If you did, you would be right on track. So I'll walk you through doing that again so you'll be better equipped to go through it in your own assignment. We have, of course, Hess's Law, change of H being equal to the sum of the molar enthalpies of formation. Let's see. This is N here, delta FH of the products minus the sum of the molar enthalpies of formation of the reactants. Okay, now remember, when you do these Hess's laws, you never include pure elements. And in this case, there aren't any. We have compounds, we're good to go. They'll both be included. So we take this and we say, okay, we have to take the number of moles in the reaction, which for products, the dinitrogen tetraoxide, there's 1. So I go 1 mole. And I times it by the molar enthalpy of formation of dinitrogen tetraoxide. That's going way back to this thing, which again, it's been a little while, right? Dinitrogen tetraoxide right here. That is the molar enthalpy of formation that we're working with. So write that down. It is positive. Remember, positive or negatives are very important when it comes to enthalpy changes. Kilojoules per mole. And now I need to take that and subtract the sum of the molar enthalpies of formation of reactants. There's only one reactant here, so that's pretty easy. But I times it by the 2 moles that are reacting. Then I need the molar enthalpy of formation of nitrogen dioxide. So same thing, going back into your data booklet. Nitrogen dioxide is over here, right about there, right? So I'm going to take that number. So we go back over, plug it on in. And it is positive 33.2 kilojoules per mole. When we go through that process, moles cancel out for both scenarios. That 1 mole and 2 moles are exact values, which means that they don't impact significant digits at all, right? So ultimately, this is just an adding and subtracting type scenario, which means your significant digits need to follow the rules for adding and subtracting. The precision follows the least precise value. Both of these changes are to the tens place. So our answer is also going to be the tens place. Delta H, therefore, for this reaction is equal to negative 55.3 kilojoules. Now that negative number means that we're dealing with an exothermic reaction. In other words, this enthalpy change needs to be written as a product. So ultimately, I would put that beside delta H equals negative 55.3 kilojoules. You could also include it right in to the reaction if you want, if that makes a little more sense. And I'll show you what I mean by that when we get in the context of a question. But please be aware that that needs to be a step when you're analyzing something in terms of temperature changes and you're not given a reaction that has the enthalpy change incorporated into it. All right, here we go. So our first case scenario is we're going to heat up the system, which means we're adding energy into it. To recap the system so that you have something to look at, and I usually do this so I can visualize it. 2 nitrogen dioxide gas is at equilibrium with dinitrogen tetraoxide gas, and I'm going to write the kilojoules in here. So plus 55.3 kilojoules. And there we have it. Now, heating up the system means that I'm adding even more energy. Remember what a system naturally does. If you add energy, it wants to oppose it, which means take it away. How do you take it away? You react it. In other words, we are going to favor the reverse reaction. Now, we don't see any sudden increase or a sudden decrease in concentration here. I'm not adding or taking anything away. So it's going to be more of a gradual change. But that dinitrogen tetraoxide is going to decrease because we're using it up as we use up the added energy. And it's going to go down by about a factor of 1. So I'll try to draw in something similar to that until it flattens out for the resulting equilibrium. Vice versa, the nitrogen dioxide is 2 moles, right? So it's going to go up by a factor of 2. So we'll draw that change first, going up a little steeper until it flattens out at equilibrium. Once again, just write it in. This is a times 2 versus the dinitrogen tetraoxide is going down by a factor of 1. The graphs themselves are not ridiculous to draw. The hard thing is predicting the shift. Which way is it going? Let's do one more example, and hopefully this can help you out a bit. Cooling the system down. Again, with temperature, I really find for me, I write down the equilibrium equation every single time because I find if I don't do that, I just get a little bit lost and a little bit confused about what's happening. Whereas if I write it down, I'm visualizing it as a new scenario without getting stuck with what happened before. If we cool this system down, we're going to take energy away. So we're decreasing it. Okay, what's the opposite of that? The opposite of decreasing energy is making more, increasing it. So the system naturally says, whoa, you're taking away energy. I need to make more. How do you make more? You favor the energy to be produced. In other words, in this case, we're favoring the forwards reaction. The forwards reaction favors means we're going to have more dinitrogen tetraoxide going up by a factor of 1. Oopsies. There we go. And then it levels off. Vice versa, the nitrogen dioxide is getting reacted. It's getting used up. Going down by a factor of 2. You can't really see a visual of going down by 2, but imagine it is, and we'll write it in times 2 versus times 1 to show that change. Notice they are in opposition to each other. If one side of the equation goes up, the other side goes down, and vice versa. There you have it, guys. Effects of temperature on an equilibrium. Now, here's a difference from concentration. And this is really important. When you mess with temperature, you do change the values of the equilibrium system. Okay? So please keep that in mind. The reason why is you are causing a more permanent shift. And by changing the actual energy that's in there, you're forcing the equilibrium to shift and stay shifted rather than go back to finding that nice sweet spot of an equilibrium. Now, ultimately, if you end up with a favor of the forwards reaction, whether it's endothermic or exothermic, if that's what you end up with, you're going to end up with more products than you have reactants. So when you think about equilibrium laws, and let's see if this is my pencil right here. If product concentrations are over the reactant concentrations, if the end result is favoring the forwards reaction, you increase products, therefore Kc is increased too. So that means that we end up with a changed equilibrium constant, different than with concentration. This is temperature. Vice versa, if we end up favoring the reverse reaction, so again, equilibrium constant is the concentration of the products over the concentration of the reactants. If I increase the reactant concentration and it stays there, right, because this would be a reverse reaction, then equilibrium constant in turn, it is an inverse relationship, will go down. Alrighty? So takeaway, if you change the temperature, you will, yes, absolutely, always change the value of the equilibrium constant. Okay, a couple questions directly related to temperature changes on a shifting equilibrium. Please go back. You can do the last question from number 1. You should have already completed A, B, C, D by now. Now you're on to E. And you can do the next question on number 3, which is D. Okay, there we go. Hope that goes well, guys. Talk to you soon.